Okay, I think we can start right now. Hello everyone. Today we have Simin Liu from Carnegie Mellon University, and for her talk, Global Planning for Contact Rich Manipulation. Simin Liu is a recent PhD graduate from the Robotics Institute at Carnegie Mellon University. Her research combines machine learning with model-based planning and control, spanning contact rich manipulation, safe control, and error robots, and adaptive local motion. She has published in Coral, iClear, and TRO, a lot of top-tier conferences and journals. So, and also she received her bachelor degree in EECs with a highest honor from UC Berkeley. And so you can start right now.
Okay, thanks, Jinzo. Yeah, I appreciate the opportunity from Professor Tran and Jinzo to come present to all of you guys. I know there's great work being done in dexterous manipulation at Duke, so I'm excited to share some of my recent work and maybe discuss as well. So, yeah, the presentation will be on one of my recent projects, Global Planning for Contact-Rich Manipulation, which I did at the Robotics and AI Institute as an intern, and also collaboration with CMU Robotics Institute. Okay, so let's begin with a roadmap for the talk ahead. So I will start with motivating the problem and also motivating the solution class, which is using contact-rich manipulation and global planning. And then I will also talk about what makes global planning for contact-rich manipulation hard in a technical sense and get to the insight, which is that we can make this problem a lot easier if we choose the right discrete decision space, which I hypothesize is reachable sets. And then I will cover the methodology, which is how we build and search over this graph of reachable sets. And finally, I'll talk about results on hardware, limitations, and also future directions for research. Okay, to begin with, why contact-rich manipulation? Why is this a promising or important paradigm within manipulation? So to define it first, CRM is manipulation which leverages complex object to robot or object to environmental contacts. So object to robot contacts are called intrinsic dexterity typically, and object environment are called extrinsic. And so here are two examples. On the left, we see dexterous in-hand reorientation. So it's using a lot of different contact-rich skills and motions to reorient the cube, like pinching, and then sometimes it's flicking with one finger. And on the right, we see spot, which uses intrinsic and extrinsic dexterity to flip up this very heavy tire. So it's kind of bracing it against its leg and torso and also the floor. And the reason why CRM is important to manipulation is that it gives us versatility and generic manipulation without using specialized hardware. So for example, we can manipulate small and intricate objects and also really bulky and heavy objects like tires using pretty general purpose hardware like the hand and spot. So there are no task specific end effectors or limbs being used here. And that begs the question, why is it hard? So there are three classes of approaches to this, imitation learning, reinforcement learning, and model-based planning. And they all struggle along some aspect. For one, in imitation learning, it's really hard to scale the data collection. Teleoperation, for example, is manually intensive. And recent work exploring retargeting human video demos has the promise of scaling massively, but it tends to be brittle on hardware. For example, in this recent work from Stanford, they've tested this and validated the retargeted plans in simulation, but not on hardware. So I think it's an open question if they will transfer readily to hardware, and I suspect that they may not. For example, For one, you do not get force information from retargeting, and that's key to contact-rich manipulation. So what about RL? So RL has seen a lot of success, but it requires extensive simulation on the order of years. So the typical RL approach is to domain randomize in sim and use a lot of training. So we see two examples here. An earlier example, Dactyl from OpenAI in 2020, which used 100 years in sim, and a more contemporary example from NVIDIA called Dextream, which used less data and compute, but still a lot. So what about model-based planning? So global model-based planning is not mature. I would say that local model-based planning is pretty mature. We have things like gradient-based trajectory optimization, sampling-based MPC, and they work pretty well with contact dynamics. But the issue, obviously, is local planners get stuck in local minima. So an example of this is on the left, where the spot is supposed to push this chair to the other side of this cabinet, and it wants to go around, or it should go around this row right here, but it's found this local minima here where the chair is close enough. And then human has to come and get it unstuck. And the reason is because it's using local planning, or essentially sampling-based MPC with a simulator in the loop. Okay, so what about global planners? The state of the art in global planning for contact-rich manipulation is the RT family of planners, and these obviously seek feasibility and not optimality. So they don't have any sense of optimality. You cannot give it a cost function and improve upon it. So in this case, you see with bimanual reorientation, RT finds a really poor roundabout path. And that's pretty characteristic of its performance in general. And so we want to work within this global model-based planning paradigm, but specifically, we want to introduce global plan optimization. And to understand this, we need to dig a little deeper on what makes global planning difficult for CRM. So global planning for CRM is a hybrid problem. It has discrete and continuous components. So for long horizon planning, like we consider in this presentation, the plan has to make and break contact multiple times. So the discrete component is deciding when to break contact, and the continuous component is planning how to move while maintaining contact. And as I see it, there are two challenges with planning for hybrid systems. The first is that the discrete portion suffers combinatorial explosion. And this is especially true for longer horizon planning. So that makes it very hard to optimize a discrete sequence. And shown here, we have a 2D in-hand manipulation example where the fingertip placements are the red dots. And in this tree, we are enumerating sequences of regrasps, essentially. The second challenge is that the discrete and continuous components are coupled. So the quality of, say, the continuous segments, for example, this one, depends on the discrete sequencing, like the regrasp that came before the segment. And the key insight I want to introduce in this presentation is that the right choice of discrete decision space can tackle both challenges at once. So let's keep these two challenges in the back of our minds while we go and explain what the right discrete decision space is. So what are some examples of discrete decision spaces? So they kind of range from low level, very fine-grained enumeration to higher level spaces that may be hand-defined. So here's two popular examples. Contact mode enumeration is an example of low level. discrete decision space, and it defines essentially the relative velocity between two contact surfaces. So given a cube and a table, the contact modes would be cube table not in contact, in sliding contact, in counterclockwise rotation or pivot about a point, and in clockwise pivoting about a point. So the issue with low-level decision spaces is that they explode combinatorially, and discrete search becomes intractable. For high level, an example is hand-defined motion primitives, as you can see, pull block, pivot, and push. And these are more efficient, but they kind of limit the dexterity and the plan quality. So maybe we want something in the middle that is both fine-grained and expressive, but also efficient. So I propose reachable sets as an intermediate representation, which has kind of the best of both worlds. And okay, so what is a reachable set? We define a specific kind of reachable set called a mutual reachable set. And it's basically all object states reachable from a seed configuration, which is a starting grasp and a starting object state. So here in purple. All object states reachable from here using a local planner. So as I mentioned earlier, local planners for contact are pretty mature. They're stable and easy to use, and they can also explore locally in this hybrid space. Basically, they can discover neighboring contact modes, as you can see in this set. Like, this is one contact mode where the geometries in contact are the cylinder and the hand in orange, but these are different contact modes here, all discoverable by a local planner because these have different geometries in contact. We define the fingertip, the white part, as a different geometry. So we have different combinations of like fingertip and hand on the cylinder. So the local planner can discover, oh, is there any question? The local planner can discover neighboring contact modes, but of course it struggles to explore more globally. But this is our mutual reachable set. So why is this? Why did I call this an intermediate representation? Well, it is higher level than contact modes because each mutual reachable set contains multiple contact modes, as I just mentioned. And I consider it lower level than motion primitives because the MRS doesn't tell you how to move, it only tells you where you can move under a local planner. So it's less prescriptive than motion primitives. And so when you have mutual reachable sets, the global planning problem becomes sequencing them and planning within them. So as a preview, we're going to be covering our object workspace in mutual reachable sets. And then when a query, start to goal, comes in, we want to figure out which sequence of MRS to reach them, right? In this case, it could be purple, yellow, blue, and then pink, or we could just go purple and pink. So we want to figure out the sequence, and we also want to know how we move within each of these sets. So it's discrete sequencing and continuous motion within sets. So going back to those two challenges for global planning on hybrid systems, how does this MRS thing solve our two challenges? So recall that the first challenge is discrete portion suffers combinatorial explosion, and the second one is that discrete and continuous components are coupled. So it addresses the first challenge because we search over just a few graph nodes instead of, for example, an exponential number of contact modes. So as an example, for the bimanual reorientation task, the object workspace can be covered with just 25 of these sets, which means you only have to search amongst those. So we've reduced the combinatorial complexity significantly. The second challenge, the discrete continuous coupling. So it addresses that because now we can simultaneously optimize the discrete and continuous components, which is obviously more optimal than, say, alternatingly optimizing discrete and continuous. And the reason we can do this, well, how to explain? So, yes, basically we can do both of these things simultaneously using a mixed integer program. And the integers will encode the sequence of sets, and the continuous variables will encode the motions within the sets. But the question is, like, why is that kinematically and dynamically feasible and valid, right, to plan motion in object space in these sets? Like, is this segment in object space going to be feasible on the robot? And the reason the answer is yes is that the MRS basically encodes feasibility by definition. For each MRS, it's feasible to move between any 2 points in the set, which allows us to use this object space abstraction while maintaining kinematic and dynamic feasibility. So that's why we can kind of optimize discrete and continuous simultaneously. Okay, so to recap what we've learned so far, CRM is a promising paradigm, but global CRM planning is unsolved. It's an open problem, and existing methods are either local or globally feasible, but low quality. And the core difficulty is that this is a hybrid problem, and it suffers combinatorial explosion in the discrete and also discrete continuous coupling. And we talked about how we could address both of these difficulties with the right decision space of mutual reachable sets, and how MRS basically reduce the search complexity, and they also encode kinematic and dynamic feasibility, allowing us to optimize discrete and continuous simultaneously while maintaining feasibility. So that brings us to the end of the intro, and now we can talk about the methodology, which is split into 2 sections roughly. So the offline phase of our approach is constructing a graph of reachable sets, and that's kind of like in PRM, where you construct the roadmap offline. And then the online portion is planning using that graph, but we have a hierarchical planner. And after that, I'll talk about results, and then hardware, limitations, and future directions. Okay. So first we should start with the task definition. We consider the bimanual planar reorientation task, and we developed this method as a first step only in SE2, but we'd like to advance it to SE3 in the next stage. And the task is to plan between a start object pose and a goal object region while minimizing a cost function of the following form. And this is kind of a cumulative form over discrete time steps where D is flexible. It can be, it only has to be smooth and regular for our approach. And this encapsulates a lot of different possible costs like actuation effort, deviation from a reference trajectory, travel time, and you can also penalize the number of regress because, regress segments are special. So the paradigm is very versatile. And our assumptions, so we consider prehensile manipulation for this project, aka the object is grasped. But luckily it's a wide subclass of manipulation. It includes, bimanual, dexterous hand, loco manipulation, things like that. And we also require known object geometry and a static environment because both of these things are required to build the graph at the offline phase. And lastly, we assume simplified contact dynamics or quasi-dynamics. This is assumed in our local planner. Essentially, quasi-dynamics just means you drop inertial effects, which means, so under quasi-dynamics, if you push a block, it won't slide. It'll just stop immediately. And this is a valid assumption in the slow manipulation regime that we're considering here. But it would obviously break if you considered something more dynamic like a pen spinning in your hand. And as a preliminary, I should introduce two planners that we're going to use as subroutines. So these are just good to know throughout the rest. The first one is the local planner. It's a contact-aware trajectory optimization, aka just a trajectory optimizer run in MPC form with a quasi-dynamic constraint. And this can move the object while maintaining contact. It moves the object in a contact-rich way while maintaining contact. And it's used to compute the MRS in the offline phase and used to move the object in the online planning phase. The second planner is collision-free motion planner, standard BIRT. And this plans arm motions without object contact. And it's used in the online planning phase for planning regraphs. So in our project, we assume that regraphs are executed by breaking contact completely with the object and then reestablishing contact. And they are found. This motion is planned by a BIRT. Okay, so I think we have enough context to talk about how we construct a graph of MRS. Or actually, one more slide of context. So I should talk about there's a constraint on the graph that we build. So basically, when you plan over the graph of MRS, I mentioned that you can plan using a MIP, and that will simultaneously sequence the sets and plan within those sets, as you see here. And this MIP can really only be solved quickly if you have a special graph subclass that has convex sets, convex edge costs, and convex edge constraints. So we have to build the graph of this format. Okay, with that in mind, we can begin to compute the graph by computing a single MRS first. So each mutual reachable set has a mutual reachability property, as the name would suggest, which means that you can reach between any two states within the set. And the way we get that property is by computing the forward reachable set of the seed configuration, shown here as a star, and the backward reachable set of the seed configuration, and intersecting those. So that's the green set, the orange set are intersected to be the brown set. And so what is a forward reachable set? A forward reachable set is simply all states reachable from the seed configuration. And this is in object space, all in object space. And the backward reachable set, likewise, is all states that can reach toward the seed configuration. So why does intersecting those two sets, FRS and MRS, give us mutual reachability? So if you want to get from any A to any B within the MRS, you can, we are guaranteed to have a path between A to the seed because A belongs to the forward reachable set, or sorry, the backward reachable set. And we are guaranteed to have a path from the seed to B because B belongs to the forward reachable set, and therefore we always have a path from A to B. Okay, but the most important takeaway is that we need sets with this mutual reachable property because that's going to be leveraged in planning over the graph later. Anyhow, so to compute a single reachable set, you discretize the object space, just make a grid, and then you compute the discrete FRS and BRS and intersect them. So you basically try to reach each cell starting from the seed configuration or vice versa. And then, because I said that the sets in the graph have to be convex, we will try to find a convex approximation of this arbitrarily shaped MRS using an off-the-shelf algorithm. And now that we know how to compute one set, we can now cover the object workspace with these sets. And we want to cover the object workspace because that's what is required to be able to answer arbitrary queries inside the object workspace. So we can just use a simple iterative algorithm. Basically, while the object workspace is not covered, you can sample a uncovered object state, compute a grasp for it. That will give you a seed configuration, and then you just generate a set around that seed configuration. So you can see the progress of this across iterations from 5 sets to 10 to 15 to 20. And it does a pretty good job of covering by the time we even get to 20 sets. And the last step in this offline phase is to connect all these disparate sets into a graph. And the rough idea is that the graph nodes are the sets, of course, and the edges in the graph are feasible transitions between sets. So for those transitions, we want to connect sets that we can regrasp between. And this is really simple for planar manipulation. We basically connect any overlapping sets. The idea is that in planar world, the only requirement for regrasp is that the object is at the same position before and after the regrasp. And the regrasp should break contact completely and then reestablish contact without moving the object. So obviously it's a little more tricky in SC3. And then as a preview for later, when you have a start and goal query come in, as here, you will have to incorporate them into the graph. So you just make them singleton nodes, and then you connect them to any MRS that they're contained inside. Okay. And also I mentioned that another constraint on the graph is that the edge costs have to be convex, and they have to be a function of obviously the object state, because this whole graph is in object space. And because we assumed a pretty general cost function, that may not always be the case. So we have to make it the case. So for example, if you assign a regrasp cost, that's not usually a function of the object state, right? Because during regrasp, the object is not moving. But all edge costs have to be functions of object state. So we can use, for example, least squares regression to fit a constant cost for each regrasp edge. And I can go into that more later in detail. Another example is if you took the cost to be actuation effort. So actuation effort is an actuated space, it's not a function of the object state. But it turns out we found empirically that you can fit a convex approximation of the cost as a function of object states that works pretty well. Okay, so now that the graph is built, we can plan over the graph. So the hierarchical planner we have has 2 stages. In the first stage, you plan on the MRS graph, and that gives you a object plan. So as you see here, this sequence of MRS corresponds to plan for the object. And in the second stage, you use those 2 subroutine planners I mentioned, which are contact aware traj-opt and BIRT, to translate this object plan into a control sequence. I'll talk about each stage specifically. So back to the first stage, we, as I've mentioned, solve a MIP on the graph to produce an object plan. And the MIP sequences the MRS and also plans within them at the same time. And this is where that mutual reachable property of the sets is used. So the MIP assumes that the sets have this property. So the MIP basically wants to freely plan between any 2 points within a set. And it assumes that between any 2 points there exists a kinematically dynamically feasible path, which there is by definition of the mutual reachable set. Okay. And also to introduce a little bit of terminology before the next step, when you get an object path, we call each segment of the path a different thing. So the object path alternates between like move object and regrasp segments. So the move object segments are obviously traveling inside a set, and regrasp is when you move between a set. And so to translate this object plan into a control sequence, we translate each segment independently or in sequence. We translate each segment in sequence. So first, for a move object segment, we translate it using the contact-aware trajectory optimization, which basically computes a manipulator sequence that moves the object the way we want it to. And then for the next regrasp segment, we break contact completely with the object and then reestablish contact. And that can be done using a collision-free motion planner like BIRT. So we basically concatenate all these segments together, and that gives us a control sequence from the object plan. Okay, so here's a recap of what we've learned. That's the whole method. MRS have a mutual reachability property that embeds notions of kinematic and dynamic feasibility directly in object space. So you can consider manipulator feasibility in object space and not full object plus manipulator space. And our methodology has 2 steps. So offline, we talked about how we compute a single MRS on discretized space, and then how we would cover objects workspace with these MRS and then link them into a graph. Online, we talked about answering queries using a hierarchical planner with a first stage of planning over the graph, producing an object plan, and a second stage of translating the object plan to a control sequence. And so looking forward, at the results, we can anticipate seeing a few things. So given this design of the planner, we can anticipate high quality paths for a variety of different cost functions. We can also expect high planning success rate in the sense that there will be no translation failure between step 1 and step 2 because the object plans are kinematically and dynamically feasible by construction. And we can expect fast query times because, again, the MRS graph tends to be pretty small. Okay, on to results. So to mention the baseline is part of the RRT family, something called contact RRT. And it's basically RRT using a contact-aware trajectory optimization for its extend operation. And it's state-of-the-art in terms of the task complexity that it can handle. So it can plan for bimanual reorientation. And the experimental setup is that we sample 250 start and goal pairs uniformly randomly within this object workspace. And the statistics reported are averages across this test set. Okay, so First result is plan quality. So our method, which we call GRS, produces significantly better plans for a variety of different cost functions. So compared to contact RT, it's 60% lower actuation effort, almost 70% lower object space path length, and 25% lower contact change ratio, which is simply the number of contact changes over the start to goal distance. And these are just numbers, but it's more interesting to look at the qualitative behavior. So one emergent behavior that we see from GRS is that it chooses the right grasp. So as you'll see here in this comparison between GRS and the baseline, GRS will choose a grasp that will allow it to perform the right screw motion. So here's where we start. They actually do have the same grasp, but GRS has chosen that grasp intentionally to be able to move directly from start to goal. And yeah, this is essentially what global optimal planning is, right? You choose grasps, which is the discrete part, to maximize the continuous part, which is the motion without breaking contact. So we see the benefit of global optimal planning. Another emergent behavior is that GRS decomposes a reorientation into the fewest possible screw motions. So here's a pure rotation query, starting here and hopefully ending here. So this is GRS on the left. And you can see GRS does what you'd expect, which is rotate in place. And that's kind of what a human would do. So this is a good sanity check. On the other hand, RT, yeah, takes a very long route. So for a harder and more interesting example, that's a query that requires both rotating and translating. We can see that it does decompose the reorientation into, I think, one or two screw motions. Right? So it's rotating and translating at the same time in like two very concise screw motions. Almost like the direct path from the start to the goal pose. While RT is still going. I'll just skip that. Yeah, so that's the performance. As we expected, the performance was significantly better than the baseline. So what about reliability and robustness? So we find that we get a 90% planning success rate, where planning success rate is defined as the percent of queries for which we produce kinematically and dynamically feasible plans. And that's thanks to the use of reachable sets, which encode and embed the notion of feasibility. And so you can see GRS planning for a bunch of different queries successfully. Interestingly, RT only had an 80% success rate, even though we gave it a very generous timeout. Okay, and speed. So GRS is fast. It takes 1 minute less than a minute online, on average across the queries. And it takes about 22 hours offline in simulated time or simulator time to compute the graph, which is way faster than RL, which takes years, for example. And thanks to having this small graph with only 25 sets, the online computation is really fast too. So sim to real transfer, how well does this apply to hardware? Okay. So it's essentially um, transfers to hardware pretty well, except when there are regrasps. So the transfer tends to be brittle around regrasps, and that's something I'll talk about in the limitations. But we can observe that it transfers pretty well for the bimanual task because the bimanual task is essentially quasi-dynamic. The modeling assumption holds. So here's another example. And you may have noticed there's no regrasps in these hardware examples, and that's because it gets really brittle at regrasps. Sometimes so it's key that it like regrasps at a very precise spot on both the object and the manipulator. And yeah, maybe that can be accomplished by just running our planner closed loop. Right now it's being run open loop, so we run GRS once and then basically track it, but maybe we can run GRS in the loop, replanning online. That might give us more robustness. And other limitations and direct extensions, for example, right now it's in SE2 and it can, I think I'd like for it to be built in SE3, but maybe things get a little more tricky in quaternion space. Like you have to deal with constructing sets in quaternion space and then solving the MIP in quaternion space. Other limitations are the static environment. So what if things are moving, obstacles are moving in the environment? And also we only show examples of intrinsic dexterity. So it would be nice to try extrinsic tasks. I'd love to hear from anyone interested in these problems and, happy to chat about potential collaborations. And so also thinking more broadly about applications of model-based planning to the learning side of things. I think, RL is inefficient. So it's interesting to think about how we can use planner generated plans to warm start RL. Like maybe inject them into the replay buffer. And also, IL is known to be brittle on hardware, and it fails especially at contact switches, which I said are kind of like bottleneck points in contact-rich plans. So one idea is maybe we can use planners to generate failure recovery demos at contact switches. So like so demos where the contact switch fails, and then it finds a different contact. So yeah, I find these applications interesting and would love to talk to you guys about them if you're interested.